okay? So we're reviewing all the stuff from last week. So we've got key features of rationals and the polynomial sketching, okay? So let's do them one at a time. Let's talk the key features of the rational stuff first. So we had 5 features that we wanted to find. Poles, vertical asymptotes, horizontal asymptotes, x-intercepts, and y-intercepts. You find the holes first because this is what's going to factor out. And anytime you deal with one of these rational functions, you want to factor first, cancel anything out to make it easier to deal with for all the other stuff, okay? Holes come from the factor that cancels out of the top and the bottom, tells you the x, and you plug back in to find the y. Once you've factored, then you can start finding all the other stuff. So like vertical asymptotes, it's the factor that's left in the bottom. So we have to have something with x left in the bottom, set that equal to 0, and that'll tell us where the vertical asymptote is. X and y intercepts, after you've factored, make the y equal to 0 or the x equal to 0, and then you can solve for the other coordinate of that point. Horizontal asymptote, this is the one that has the rules based on the degrees. If the top is bigger than the bottom, if the bottom is bigger than the top, and different types of asymptotes. We had 3 different types to come out to get answers for this. 3 different types of answers. We got y equals 0. We had this one that was y equals a over b. And then we had one that we said was a slant or polynomial. And this was based on the degrees of whether the denominator was bigger than the numerator or they were equal. This one was when they were equal. Which one was when the bottom was bigger than the top? Bottom bigger than the top is when you get y equals 0. So this is where our denominator is greater than our numerator. And this one down here is when our denominator is less than our numerator, meaning the top is bigger than the bottom. And the only way to get through those with how we're doing this is you got to memorize those rules based on that comparison. All right, let's practice. So I really honestly think the hardest part of this is the factoring. Once you get through the factoring, if you remember the steps that you work your way through, finding the actual features isn't terrible. It's the factoring that will usually get you before anything else. So first step, let's factor. The one that we tend to miss more often than not, there's a common factor in the top. What's common between x to the third and 9x? They both have a x in common. Then that leaves you with x squared minus 9. Down here, what's the common factor before you even try to factor it with the box? So all these coefficients have a 3 in common. Let's pull that out before we do any factoring. Because if we make everything smaller, it'll make all the math easier as we work through. Now we're not done because both of these things factor again. But we've got the common factoring out. Look for common factors first, every time, and then work into the box factoring, okay? So let's see. The top of this is going to factor into x minus 3, x plus 3. And I'm going to write that down y. And then the bottom, we want the factors of 3 that have a difference of negative 2. So that's going to be x minus 3, x plus 1. Biggest thing with the top, it is called the difference of squares, but if you were to forget the formula, remember that you could write that as x squared plus 0x minus 9 when you draw the box to factor it. Then this is x squared, and this is minus 9, and you want the factors of 9 would subtract to give you 0. So that's where you would get 3, and negative 3 gives you the 0. So that's going to be negative 3x. That's going to be positive 3x. And there's where I get my factoring. So even if you forget the difference of squared rule, which probably happen more often than not because you hadn't practiced it a ton. We could do that. And then the bottom down here, I did the same thing. I box factored, but I had a middle term. Is everybody okay with factoring? All right, so now we cancel and we see what's left. So let me actually move this over. So this x minus 3 is going to go away. So I have x times x plus 3, and I have 3 times x plus 1. That is what's left over of f of x after it's factored. This is what I'm going to use when I do the vertical asymptotes and the x and y intercepts because there's less to work with. This tells me that this one has a hole. So I'm going to take that x minus 3, set it equal to 0. That's going to tell me the x coordinate of the hole because I'm listing it as a point. So I solve this. It tells me the x should be 3. So the x value here is 3. And now I'm going to use this because I can plug that x value in and it'll tell me the y value of the hole. So to find the y, I use what's left over after I factored, and I plug in 3 for all the x's. So this is 3 times 3 plus 3 over 3 times 3 plus 1. So that is 27 over 12. No. 4 times 3 is 12. Oh, it's 8. It's 18. I did 3 times 3 times 3. Hey, don't ever do all your simple math in your head after you do all the hard stuff. Thank you. 18 over 12. And let's see, what does that reduce to? Three over 2. So we finally found the y. It's 3 over 2 or 1.5. But when you find holes, holes are coordinates of where that is. So we're going to need that space. Let's do the horizontal asymptote next, because that's the one where we need to compare the degrees. So we need to look at the degree of the top, the degree of the bottom, and see which rule we have. So the top of this one is a 3rd degree, bottom is a 2nd degree. So does that mean y equals 0? Does that mean I divide the coefficients, or does that mean this one has a slant or a polynomial asymptote? Let's go back and look. So our numerator is bigger than our denominator, so that means this one should have a slant or polynomial. Eventually, I'll show you how you can actually find these equations once we get through what we start with this week. But right now, for this, just write, I know this thing is slant or polynomial. Vertical asymptotes. We take what's left over in the bottom and we set it equal to 0 and we solve. So here we have 3x plus 1 is equal to 0. So when you have this multiplication, even though it's going to seem ridiculous, it's going to help you remember it when we have something else out there. We got to make both these things turn into 0. Is there any way to make 3 turn into 0? So that means that doesn't work. We don't have to worry about that number. But this one, there is a way to make that equal to 0. That's the x minus 1. That is an equation of a line, and that one is our singular vertical asymptote. Because remember, vertical asymptotes, you can have more than one. There's many of those factors on the bottom that work. Let's do x-intercepts next. So the key with x-intercepts is we know that the y has to be 0, right? So that means we can take what's left and we can turn this f of x part into 0. and it'll allow us to solve this. Now, does the denominator ever play a factor in this? No, because you're going to multiply this up, and 0 times anything is going to be 0. So really, we just need to look at the numerator. And the reason I brought this up, where we need to talk about this number in the front, this is one that we'll easily miss, that this one actually has 2 x-intercepts. Because to make this expression equal to 0, I need to figure out what makes x equal to 0, and I need to figure out what makes x plus 3 equal to 0. So what makes x equal to 0? When x is, that's right, that's exactly right. When x is 0. But sometimes you have to say that one out loud, or at least in your head to yourself, because you'll look at it and you go, wait a minute, is that really an answer? That one is an answer. To make that front part 0, you make x actually 0. That is one of our x-intercepts. Then we're going to find the other one over here. It'll tell me the x value. That's the -3. So this one had 2. And there's our x-intercepts. Now we're talking y-intercept. You actually don't need to do any math at this point, because you got a special number here that guarantees that you know what the y-intercept is. If you ever get an x-intercept of 0, 0, that's also the y-intercept, and you're only ever going to have one. I want to plug it in to show you that it works, okay? Because what we know about y-intercepts is we know the x value. We know the x is 0. So to find this, we're going to say y equals, we're going to plug 0 into all of this. 0 times 0 plus 3 over 3 times 0 plus 1. So 0 plus 3 is 3. What's 0 times 3? 0. Does it ever matter? Does it matter what the bottom's going to be? Nope. 0 divided by anything is always going to be 0. But we're still do the bottom. 0 plus 1 is 1. 3 times 1 is 3. That's the worst 3 I've ever written. So we do get the 0 that we'd intended out there, which tells me this is that feature. But if you ever do the x-intercepts, you get 0, 0 as an answer. That has to be the y-intercept. It's almost like you can skip the algebra for that one. So those are all the features. Anybody graph any of these things and look at them in Desmos as they were doing them last week? So let's look at it. This is what the picture looks like. So here's our x equals -1 asymptote. Here's our x-intercept here of -3, 0. Here it is again right here at 0, 0. There's the hole. That looks like it's 3, what was it, 1.5? And all those things match up. Now Desmos doesn't do a great job showing you holes. You'd have to actually know where the x value is and click on it. But what I really wanted to point out about this one, when we talk about that slant asymptote is in here. There's actually a line that splits this apart. I have to move it around a little bit. About like that. That divides these halves, but instead of being horizontal straight across, it actually gets slanted. And when we're able to find the equation for this thing, this is actually an equation of a line, like a y equals slope x plus the y-intercept, mx plus b. You can actually find the equations of these things so you know where they're supposed to be. Let's do the second one. With our sketching polynomials, we use the lead coefficient to determine which way the ends would point, based on what we knew about power functions even power functions, which are even powered functions. Both ends either pointed up or down, depending on whether the coefficient was positive or negative. Odd power functions pointed opposite directions, down and up or up and down. And that was something that we had to memorize. Now, really, we used that to help us with the sign charts. We understood if we were doing this correctly. So let's talk about this one and talk about its lead coefficient first. What's the degree of this polynomial? Well, lead coefficient is, the lead term is 2x to the third. Its degree is 3. If it's an odd number, you know that the ends are going to point opposite directions. One will point down, one will point up. Now we look at the coefficient. The coefficient is 2. And the important part of that is that it's positive. Positive and odd tell us that the left end, which is what this negative infinity means, will point down, and the right end will point up. Now, the way that we had done the notation, which I am perfectly fine with you guys doing it this way if you're going to list it down. The left end points down, and the right end points up. That means the same thing because we're drawing conclusions for this. Because what it means is that in our sign table, when we get past the last 0, we know that we should get an overall negative because the only way it can point down is it's got to be below the x-axis because it has to have already crossed it and be down there negative. Far right end in our sign table should be positive overall because that's the only way it can point up is it's gone through the x-axis and it's above it. So the big thing with this was finding the zeros and creating the sign chart. So how do you factor that? What does it have in common? It has an x. I'm sorry, it has a 2x, doesn't it? That's the tough part of this one. And now this will factor nicely because it's the difference of 2 squares or with the 0 in the middle. What are the factors of 16 that subtract and give you 0? 4 minus 4, which means you're going to get 2x. One of those is the minus 4. One of them is the plus 4. What does that mean the zeros of this function are? Now, how many do we think it should have based on its degree? It should have, we think it should have 3 because it's a third degree. It should have at least 3. It won't have 4. At most, it can only have its biggest degree, okay? Now, when we go through and we find zeros, the reason we're calling them zeros here is what makes that equal to 0? Just like what we were doing over here, when we were setting these things equal to 0, we set each part of this equal to 0. So 2x equals 0. X minus 4 equals 0. X plus 4 equals 0. This will tell me all the x-intercepts of this factored function. So this one is 0. This one is 4. This one is negative 4. And those are points. 0, 0, 4, 0, and negative 4, 0. And I listed them up here just like that. So let's talk about what we know about this graph already, because if our overall goal is to graph this thing and use these features, if we go to make a sketch of this, we know that we have x-intercepts here, here, and here. And from this, from looking at the lead coefficient, we know that the left end should point down. And we know that the right end should point up. The only part of this sketch that we're missing is what happens in the middle. And through our practice last week, we realized that these x-intercepts, they don't always have to go through. They can go through, but they could also bounce. And that's what our sign chart helped us figure out. The way you set up the sign chart, and this one's overly simplified, these are the roots. The numbers in blue down here, these are what I'm going to test with, meaning I'm going to take this number and I'm going to replace it in here with x and figure out whether it's positive or negative. I didn't draw the whole table this time. Underneath it, I just have its overall sign. Now, the reason I included the ends, even though we did the end behavior here, it's always a good check, especially with one that's complex, to do your ends to make sure you get the answer that you know you should get based on the lead coefficient, okay? So looking at this and what we have here, we think we should get an overall negative when we plug in any number smaller than -4. So if we put the 5 here, what happens? Well, let's not worry about the actual numbers. Let's just worry about the sign. 2 times -5 is negative. -5 minus 4 is going to be negative. And -5 plus 4 is going to be positive. Negative. Thank you for keeping me honest. Negative times a negative times a negative. So we're going to get a negative times a negative times a negative. And the rule that we looked at here, anytime you get an odd number of negative signs, your overall is going to be negative. Because negative times a negative is a positive, and then you got one more negative left to make the whole thing negative. So that worked. We got our negative answer. That negative here, this is overall, means that the graph is below the x-axis. If I get a positive overall, that means my graph has to be drawn above the x-axis because the y values that are coming out are all positive. So if we continue this process, we're going to do the same thing here. But instead of plugging in that 5, I'm going to plug in a -1. So let's just write down the sign. 2 times -1 is going to be negative. -1 minus 4. Is that a negative or a positive? -1 minus 4 is negative. What is -1 plus 4? That one's positive. How many negative signs do you have? 2, and 2 is even. So anytime you get an even number of negative signs, your overall is going to be positive. So that means that our graph is above. So you can actually put that here on our sketch. This was -4, this was 0. What this means is in between these two roots, the graph has to be drawn above the x-axis. So what that shows is that we actually do cross the x-axis here, and we're above it. All those y values are positive because they're above the x-axis. If we go through and we continue this, we're going to do the same process. Plug in the 1. 2 times 1 is a positive. 1 minus 4 is negative. 1 plus 4 is positive. We have 1 negative, which means that's odd. Overall, that thing's going to be negative. And this part tells me that we're below the x-axis, and this should be drawn down here. Test the last one just to be sure that everything matches up. So we plug in the 5. The first multiplication is positive. 5 minus 4 is a positive. 5 plus 4 is a positive. So everything's positive. So we get this positive that means we're above. If you remember seeing the charts and the tables that I drew last week in the videos and the stuff in the notes, remember I kind of laid it out much bigger. If you're getting more comfortable with this, making it more compact is fine. If you're not, making it bigger to match, you can still do that, okay? Questions on that one? I think we're doing pretty good. All right, let's go through this one a little bit quicker. So zeros. How many zeros are there for this one? There's going to be one for the x plus 3, one for the x plus 6, one for the x minus 7, and one for this negative x. Don't forget about when there's an x in front, you've got to count it. What makes x equal to 0? When x is 0. So you actually get 4 out of this. There's one here, 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 and here. Now, if we go to try to figure out the end behavior, this one's not multiplied out, so you can't see the lead coefficient. You could take time and multiply that out. You probably could do that pretty quick, but we only care about the first term. The power is going to be defined by how many x's there are in this factored form. So there's 1, 2, 3, 4. So that means our lead coefficient is going to be x to the 4th, because there's 4 x's in that factored form. Is it going to be positive or negative? And this is another one of those counting the positive and negative signs. So this x is positive, this one's positive, this one's positive, but this one's negative, right? So that means we have one negative. Overall, that thing's going to come out as negative x to the 4th. If you took the time and drew all your boxes and multiplied all 4 of those things out, the first term you would see would be a negative x to the 4th. So that means that this is a 4th degree polynomial, and the lead coefficient is negative. So let's talk about what the 4th degree means. 4th degree means that these ends are going to point in the same direction. Anything even powered points in the same direction. Either both ends point up or both ends point down for our graph. So I want you to think x squared. Which way did x squared point? Just a normal x squared. Did it point up or did it point down? It points up, right? If you make it negative, you got to think a was negative. That flipped it and made it go downward. So because it's 4, I know both ends point in the same direction. Because it's negative, I know both ends are going to point downward. So, and again, I'm not worried about this notation per se. I include it because it was in the notes and it's something you might see. As we go to the left, the graph goes down to negative infinity. As x goes to the right, which is where positive infinity is, our graph is, we go to the right, we're going to go downward to negative infinity. This notation means the same thing as this picture. And since we're just using that information to get to our final answer, I am okay with either way that you put it on there. Don't feel restricted that you have to list it like this, but I want you to understand what that notation means as well. All right, sign chart. So we need 5 zones because we've got 4 roots. So we need to list our roots in order. This is the one as you go through this process that'll catch you when you make a sign chart. Make sure you put your most negative number first and count them in order, because it's really easy to go 0, 7, negative 6, negative 3, right? It's really easy, okay? So just be really cautious at that point. That's all. After you get in behavior and you kind of get all your zeros listed out, I always say it's a good time to, you know, I don't know, count the dots in the ceiling for 10 seconds or something, just to kind of clear your memory and go, okay, put these in order, because it's a real easy mistake to make as you go faster. Pick some test values. Now, we are pretty darn sure, we know, because we did the lead coefficient right, that both of these should be negative. We're going to check them just because it's always good to make sure we have all the signs that we're supposed to. Because this negative x is going to be tricky. So we should have 4 signs in each one of these regions. If we plug this negative 7 in, what is negative 7? Is it positive or is it negative? It's positive. that negative with the x is going to flip the sign of whatever we put in there. Now, -7 minus 7 is a negative. -7 plus 6 is a negative. -7 plus 3 is a negative. And that works because we have an odd number of negative signs. So we do this, and this means that our graph is below. If you don't want to put another negative there and you want to write the word below or above when you're done, that might be beneficial because that's kind of our overall statement. I know that when I go to sketch this thing, pardon my sketching. Sketching is exactly what I mean. Out here at -6, I know this end goes downward. That's what that negative tells me. It's below the x-axis at that point. How far do we need to go? 7? So we had 7, 0, and -3. And what we're doing inside this, we think that this one, we know this one should go down too, but we're still going to check it. We've got to test in between each one of these spaces to see what happens. Because there's pattern here, and we can talk about the pattern at the end. That kind of makes the sign chart even easier. But if there's one you want to be sure of, you always want to check it with your sign chart, because the sign chart's going to come in handy for something we do later on, which is why we're emphasizing it here. All right, -4 means we're going to get a positive for the first thing. -4 and -7 is a negative. -4 and +6, that turns positive. -4 and 3 is a negative. So now we only have 2 negative signs, which means that's going to turn down to a positive, and our graph is going to be above. So when we go to sketch it, we know in between the zeros of -6 and -3, our graph is above. Okay. I noticed, did I put any markings on the y? Because I'm not having you find y values at that point. Could you calculate y values for some of these points as we went through? Yes. But this is a sketch, and the x and where it's above and below are the important parts of this right now. Just knowing that the y is positive will work for what we're looking for. All right, let's keep on going. Let's fill them all in. So -1, that's going to give us a positive, a negative, positive, and a positive. So overall, since we have one negative sign, that's negative, and this thing is below. That one should be positive, but let's check it all out. So we're going to plug in 2. So we're going to get negative, negative, positive, positive. Even number of negative signs means that this is above. And then the last one we'll plug in is +8. So we're going to get a negative, positive, a positive, and a positive, which checks because that means it should have been below. So if we go through and we finish our sketch, none of ours bounced this time. And we are below between -3 and 0. And then above here. And we kind of pieced it together to kind of look like a polynomial, but that's okay. And just put your zeros on there. That was -6, -3, 0, and 7. I know we've been going for a while. Let's finish this last one. We'll take a break. That one looked more intimidating? Only this one looks more intimidating because of the powers, okay? Let's talk about what powers mean real fast before we do this one. What does 3 to the 3rd mean? Now, what's the answer, but what does it mean? It means 3 times 3 times 3, right? So therefore, what does x to the 3rd mean? Now let's do one like this. What does that really mean then? It means x minus 1 times x minus 1 times x minus 1. It means that what we've done is this is a simplified set of this. This is factored form, but how many times should I really write this x minus 5 in parentheses? I should really write it 4 times. I should write this x plus 3 4 times. I should write this, you know what I'm saying? We're shortening it. That's what powers do. Now, this won't affect the zeros. That's called multiplicity, and we're going to work towards that as well. You can have a 0 show up in your factored form more than once. This x minus 5 shows up 4 times, but we still can only cross the x-axis once at that 0 of 5, 0. So this one tells me that 0. It doesn't affect doesn't affect what I'll see on the graph. It just affects what the algebra does. That means that all of these do the same thing. You're going to get this -3, -6, +2. There's still only 4 visible zeros or x-intercepts on this graph, even though the powers on them are weird. And rationalize through that, it makes a little bit of sense. Even though that x minus 5 should be written 4 times, I still can only cross the x-axis once at that spot. That's as far as I can get there. We'll get into that in a second. Now let's talk about the lead coefficient. And this is one where that last method works really well. So we've got to figure out how many times x appears. But this is where this gets weird with powers. We see this as 1x, right? But how many times should that x really be written? X minus 5 to the 4th really means x minus 5 times x minus 5, x minus 5 times x minus 5. Meaning if we're counting x's so we can figure out the power of our lead coefficient, that x is really in there 4 times. So when you get powers, you've got to start counting the powers for your lead coefficient. Meaning we've got 4, 8, 11, 14. The degree of this is actually 14, not 4. Because if you wrote it all out, it's all about how many times you see x, just like what we did here. We had 1, 2, 3, 4. But none of these had powers bigger than 1. They were all powered 1. They were only written in there 1 time. If you wrote this out really long, like what we were doing right here, 14 times is how many times you would see the x, because you've got to add up these powers. 4, 8, 11, 14. Now, luckily here, there's no negative sign, so they're all going to be positive. So that's going to be a positive 1. So the degree is 14. The coefficient is positive. So because it's 14 and even, it means they both point in the same direction. And because it's positive, it means they're both going to point upward. And that means these 2 spots right here get positive infinities. They're all both going to go up forever. Now you think that we're going to do the sign chart for this one. And you'd think this sign chart's going to be any tougher, but these powers actually make the sign chart a little bit easier. So we know where we cross the x-axis. And we're going to pick some test points in there. Now, why did I pick -7? I don't think we talked about this. I picked -7 as a test point here because it's to the left of -6. I picked -4 because it's in between -6 and -3. Pick 0 because that's in between -3 and 2. You got to pick numbers that are in between it, or on the ends got to be bigger than or less than that number. So let's go through and talk sign table, because this is where some of this interesting stuff happens. You actually only need to worry about plugging the number into 2 of these, because 2 of these answers will never change sign. So let's look at the type of powers I have. I have powers of 4 and I have powers of 3, right? What happens to any number you take to the power of 4? Like take negative 10 to the power of 4 on your, well, you don't have calculators out, but on your calculator on your screen. What's going to happen to it? It's going to turn positive. Anything to an even power, any root to an even power will always be positive. Meaning that when we look at this, these two right here, these first two, I don't need to plug numbers into them. They're never going to be negative. It does not matter what number comes out of that subtraction or that addition. When I take it to the fourth power, it's going to come out as a positive number. So those first two signs, I can pre-fill in without ever plugging in a number because they have an even power. The only thing I need to test is I need to test the N2 to see if they're going to be negative or positive because they're odd. Odd powers, if it's negative, if it's a negative number to an odd power, is going to be negative. If it's positive, it'll be positive. So it's just ruled by the subtraction or addition. So that means when we come in here, we're going to go -7. -7 plus 6 is a negative number. So that means that term is negative there. -7 minus 2 is a negative. And we thought, I didn't draw my graph yet. Let me do that. From the end behavior, we know that that one should have been going upward. That's an even number of negatives. So that means it's going to be positive or above based on our sign chart. But what happens is when we start having these powers, anything comes out with an even power is when we don't ever have to check. We just need to check the odds like we did before. So let's go through and fill the rest of this in. So -4 plus 6 is a positive. And -4 minus 2 is a negative. I'm going to fill in all the signs and then we'll go back when I can delete it. 0 plus 6, that's positive. 0 minus 2 is a positive, is a negative. 4 plus 6 is still positive. 4 minus 2 is positive. And 6 plus 6, still positive. 6 minus 2 comes out as a positive. So now let's look at the overalls, see what happens here. Only one negative, meaning that thing's negative. And this is going to be below. So we need to go to -3, 2, 3. And we know that we cross the x-axis and we go below. I'm doing a bad job of making them match. There, close enough. Hey, draw your dot a little bigger if the sketch doesn't meet up. All right, same thing happens here though. We get one negative, meaning this one's also below. So what happened at this 0 of -3? Because we know it touches the x-axis at -3, but did it go through it? It bounced off it, kind of like a tennis ball hits the floor. It hit that 0, but then it stayed negative. It stayed below the x-axis, meaning we're heading to +2, which is out here. It bounced off this thing and stayed negative and headed back to that one. I'm doing a poor job of making no corners, but I think we're getting the idea. Then here, we get all positives for both of these, meaning that our graph is going to be above and above. So we're right here. So we go from below to above at -2 and it crosses over. And then we come out here to 5. And we tilt down to 5 and touch again. But after 5, do we go down below the x-axis again? No, it bounces again. And we get the end behavior of upward like we suspected.